Hey everyone, welcome into this video on antiderivatives and integrals of arc-trig functions. So once we know derivatives, which we computed in the last lecture, we can automatically apply the fundamental theorem of calculus, of course, and we have learned then, we already know, some antiderivatives. Now they aren't necessarily the antiderivatives of the arc-trig functions themselves. So I'm just going to write down a couple of them here, the three major ones. So I hope we remember that the derivative of arc sine of x is equal to 1 over 1 square root of 1 minus x squared. And so what this tells us then in terms of antiderivatives is that the antiderivative of square root 1 minus x squared square root dx must be equal to what? Well, how do? You integrate both sides, right, with respect to dx, and then you get arc sine of x plus c. On the same token here, the derivative of arc cosine of x, this is one you should have worked out yourself, you get negative 1 over square root 1 minus x squared. And this then tells you that the antiderivative of negative 1 over square root 1 minus x squared dx is equal to arc cosine of x plus c. And then you start to wonder, because look at these are, this one's just the negative of this one, right? And so you can imagine, or here you could say that this antiderivative of negative 1 over square root 1 over x squared dx, square root of 1 minus x squared dx, that this could be equal to negative arc sine of x plus c. And you start to then question reality, right? You start to wonder, how is it possible that this is equal to this? Is that even possible? And the answer is yeah, of course it's possible. But what's not so clear is that in this case, these two plus c's, these are not the same, right? These would be different. These would be slightly different. So remember, arc cosine and arc sine have basically the same graphs. The difference being that one of them is the reflection in some sense of the other one, has a minus sign. And then they're shifted, right? So the plus c's will be different numbers. But otherwise, these two graphs, arc cosine of x and negative arc sine of x, so the reflection, those two graphs have the same general shape. They have different y-intercepts, right? So then you would just shift them to get the right answer there. Now the other one that we'll review here before we go on is the derivative of arctangent. So the derivative of arctangent of x is equal to 1 over 1 plus x squared. And this, of course, implies then that the antiderivative of this fraction, 1 over 1 plus x squared dx, must be equal to arctangent of x plus c. All right, and so we will use our favorite versions of each of these in the next couple examples. So I have 3 examples for us. So let's get to them. The first example is this one. It's the integral from 0 to 1/4, so definite integral here, of 1 over the square root 1 minus 4x squared. So I titled this lecture Antiderivatives, and the reason is because we're going to do this definite integral by using the fundamental theorem of calculus, right? So we are going to start by finding the antiderivative of the integrand, and then we will use the fundamental theorem and plug in these boundaries. So the first thing that we need to do is deal with this. So this looks a lot like either arc sine or arc cosine. It's 1 minus something squared, but the something squared is not just an x right now. It's got something else there, right? So this whole thing, I'm going to want this to be a u squared, all right? Because if this is 1 minus u squared, then if that were true, right? If that were true, if this was 1 minus u squared, and if we have our du, then this could just be written as the arc sine of u. Well, if this is going to be u squared, let's just look at this. If u squared is going to be equal to 4x squared, then what's u have to be? Well, u, of course, has to be, we could write this like this, right? 2x parentheses quantity squared. U should then be 2x, right? And then remember, whenever you when you choose a u for a u substitution, you do not get to choose your du, you have to compute it. So our du is going to be 2 dx. And that's right. Now, do we have it? Is it going to be acceptable, right? And the answer is this part, we made it that way, so that's good, right? The 2 dx we don't have, but this is easy to fix. We put a 2 here, we divide out by a 2 out here. Integrals are linear, so we don't have to worry about any problems with that. And then this whole term becomes our du, right? That's it. Now, the other thing that we need to do is we need to change our boundaries now so that we don't have to worry about it later, right? So when x is equal to 1/4, what happens to our u, right? So when x is 1/4, u of 1/4 becomes 2 times a quarter, or 2 times a fourth, which is a half. And when x is 0, so u is 0 here, then what do we get? 2 times 0 is 0. So our new bounds are 0 and 1/2. So our integral now becomes 1/2. This one has to stay here, right? That one did not get absorbed in our du. 1/2 times the integral from 0 to a half of 1 over square root 1 minus u squared du. This is nice. We know exactly what the antiderivative of this is. So we have our 1/2. We apply our fundamental theorem of calculus part 2. Antiderivative of this is arc sine of u. And then we have to plug in our boundaries, right? So we plug in then u equals 0 and a half. We never have to go back to x. We've made the change everywhere. All of our variables were changed, right? So we're good there. And now we just plug in. So this is then 1/2 arc sine of a half minus 1/2 arc sine of 0. And at this point, we just need to remember what angle has a sine value of 1/2, and that's going to be pi over 6, right? So pi over 6 is the first angle. So sine signs up and cosine counts down. I'm sure you remember that, right? So this is then 1/2 times pi over 6 minus 1/2 times sine of 0 is 0. So that's a 0. So then this just leaves us with pi 12ths. And that's the answer to our definite integral. All right, on to the next one. This one's a little bit more symbolic. So this one we want to try to integrate, find the antiderivative of 1 over a squared plus x squared, where a is any real number. Let's say, I'm going to change it. Let's make a positive number since it's squared, right? So let's make a positive number. And okay, good. That's what we want to do. If we go back to our first page here, of all of these, the one that our current problem looks the most like is this one, right? 1 over 1 plus x squared. We don't have a 1 though, so we're going to have to change this. We need to make this be a 1. So what we can do is we can try to factor out this a squared from the bottom, and we can just take it all the way out of our integral. 1 over a squared, way out here. Integral of 1 over, we took away a squared from here, so that's just 1. If we take away a squared from here, though, this becomes x squared over a squared dx. And then we want to try to make a u sub again, right? So once again, this is very similar to what we just did in the last problem. We want that thing, that ratio, or that, yeah, a ratio, x squared over a squared, to equal u squared. Then we want that to be our u squared so that this becomes an arctan, right? So what does it have to be? Well, we're going to set our u equal to x over a, just like we did before, All right, and again, we don't get to choose our du. So du has to be 1 over a dx. And then the question is, do we have it? Well, actually we do. We have two 1 over a's out here. We have 1 over a squared. So let's take one of those away and group it here with our dx to make our du. It still leaves one of them out here though, right? So we've still got this one out here. Okay, and at this point there's no limits, so we don't have to worry about that. We can just rewrite this integral now as 1 over a integral 1 over 1 plus u squared du. This whole thing becomes du. All right, that's arctangent of u. That's exactly arctangent of u, right? So now we have 1 over a arctangent of u plus c. This is an antiderivative, so we cannot forget our plus c. But we also can't leave u in here this time, right? When it's an antiderivative, you have to get it back in terms of the original variable. And so we just have to plug this back in for u. And we end up with our final answer here being the antiderivative of 1 over a squared plus x squared dx is equal to 1 over a times the arctangent of x over a plus c. All right, so there's two problems down. I got one more for us. Feel free, by the way, if I'm going too fast, pause the video, pause and ponder, as our friend over at 3 Blue 1 Brown would say. This time I have a little more intense looking integral here. This one is the arc sine of x divided by 1 over 1 minus x squared. And yeah, just looking at this, it's not clear, right? So one thing that we don't have yet, and we won't ever really have, is a product rule for integrals. We'll have something kind of like it, but we don't have it. We don't have it yet, right? So we don't know how to deal with products. All we know how to do right now is make u subs. So when we look at this, we want to try to pick a u for which we have the du. So we want to pick a u so that our derivative comes out of it, right? That we have the derivative. If we pick this bottom function to be our u, are we going to get back an arcsine? No, we're not, right? So we want to do the opposite. We want to choose this to be our u, right? We want this to be our u, and then we want to see, do we get the proper antiderivative back? So let's check. If we let u equal arcsine of x, we do not get to pick du. We have to compute it. Du is the derivative of this, which is 1 over square root 1 minus x squared times dx, differential, and that we definitely have, right? So this whole thing is right there, right? So that's what we got. So that becomes u du. That's beautiful, u du. All right, let's plug in our boundaries so that we don't have to go back to these, because again, this one's a definite integral. We don't want to have to go back if we don't want, we don't want to go back if we don't have to, right? So we need to know, what is u going to be when x is 1/2? We just did this, right? So the arcsine, these are the same boundaries we ended up with before, just by chance. That's coincidence, but that's pi over 6. And then u of 0 is, of course, arcsine of 0. That's just 0, right? So that's 0. All right, now we plug in. Our integral becomes, we don't have any factors that we added or divided out, so that's all good to go. Our new boundaries are 0 to pi over 6, and our new integrand is just u du. Oh man, that's a breeze, right? So this then just becomes 1/2 u squared, plug in the boundaries, fundamental theorem of calculus in action right here. Don't ever forget that when you use the fundamental theorem, and the answer becomes pi squared over 72. And that's the answer to this integral. All right, so there's 3 examples of integration using or antiderivatives, integration. It's all kind of related by the fundamental theorem of calculus, using these Arc-Trig functions and their derivatives, antiderivatives.